So that's a special type of two location problem when there was no work in and no work done by friction. So because that was how we ended, that's when it was going to be 1 equals over 2. Now what we're going to do is we're going to come back to, well, what if there is work in, or what if there is work being done by friction? So that's kind of actually how we started off. There was a packet. In my attempt to quickly locate that packet, I was unable to locate that packet that had work on it where we defined the energies, but it was the very first thing on the very first day that we came back, and we did 2 of the pages together, and the rest was a virtual day assignment. It's called like work, power, energy, is what it was called. And in that, we talked about 4 different types of work. We talked about work done by gravity, which you said we were never going to use again. We talked about work done by normal force, which we said we were never going to use again. We talked about work in and work done by friction. Now, those are the 2 that we're going to use because in that equation that I just erased, we need to know those numbers. So in that packet you picked up today, I'm going to kind of work through some of these problems, or kind of these talking points. So in the packet that you picked up, it's in Canvas, it's called In Class Working with Intro to Lack of. I'm going to kind of randomly number these, not randomly, sorry. I'm going to systematically number these from 1 till whatever, just so when I'm on the board, we can kind of be working on this. So I'm going to have the questions up there, but I'm going to be writing the responses up here just because it's easier to see than trying to look at the screen. Okay. So back when we introduced this unit, or on work, there was a generic equation that we used. So number 1 on that packet, right? So I went through and I numbered, I don't know how many are on the first page. There's 10 questions on the first page. I should have numbered this in advance, but again. Number 1 talks, what is the generic equation that we use for work? And it's this: work is equal to plus or minus some parallel force times a displacement. And that parallel force is any force that's parallel to the displacement. And if the displacement was in the if the force is in the x direction, then we would use, the force we're talking about is in the x direction, then we use delta x. But if the force we're referencing is in the y direction, then this would be a delta y. Plus or minus is something that we're going to have to make the choice on, and we'll address that in just a little bit. Of the 4 types of works that we did at the very beginning of this unit, there were 2 that I said we were going to care about down the road. And one of them is the work in equation. So work in, number 2, is equal to plus or minus our applied force times a displacement. I'd maybe put a star next to that one because that's an equation we're going to use fairly frequently. But what that equation is this is just a modification of this. So the force that we're referencing is an applied force. And if the applied force is in the x direction, we use delta x. Now, is it possible for me to have an applied force in the y direction? Sure, right? Ooh, look at that, y direction. Then that would have to be a delta y. Okay? So that can change, but it's still going to be, this is our equation for work in. Now, when we talk about work being put in, we often reference work going into the system. So when we talk about a system, we're talking about like an object, and are we adding energy or removing energy from that system? And that depends upon what's going on there. And when we talk about that, that's whether we're gaining or losing energy comes from that plus or minus. The way back in that packet we talked about is, are they in the same direction or opposite direction? Is my applied force in the same direction as my displacement? The opposite direction. Depending upon what that is will depend upon whether it's positive, negative, or in some cases 0. So for number 3, it talks about if my applied force is in the same direction, and this is like in the words, I'm just writing kind of the reference, to my displacement, then this is going to be the plus. Okay? If my applied force is in the same direction as my displacement, then it's going to be positive. So when we have to make the choice, is it the plus or is it the minus? If they're in the same direction, then it's going to be the plus. Notice how it doesn't say left versus right, it's saying the same. Because if I have an applied force this way and a displacement this way, those are the same direction, it's going to be positive work. I'm adding energy to the system. My applied force is this way, and I'm pushing it this way, that's the same, I'm still adding energy to the system. Think of it this way. If I'm applying a force to this chair, okay, I'm adding energy to the system, which means I'm giving it energy. Energy is being added to the system. Okay, now is it possible for those to be in the opposite directions? Sure. And if they're in the opposite directions, then it's negative. Then we're removing energy from the system. That's what these things are saying. So positive is we're adding energy to the system, and when it's negative work, we are removing energy to the system. I got a sneeze I'm trying to fight off here. Now remember, in order for there to be work, we need two things. We need an applied force, and we need a displacement. I push against the board, I'm applying a force, but the board's not moving, therefore I did zero work. But and they must be parallel to one another. They must be parallel. So what if my applied force was perpendicular, that's mathematical symbol for perpendicular, to my displacement? And what that would mean is, like, my chair is moving that way, but I'm lifting upwards. Now, is it possible for an object to be moving that way and me to pick up? Yeah, it is. You know, this thing could be moving, and I'm gonna lift it up on it, but it's still, right, I'm reducing the amount of downward force. Generally, when we talk about something like that, you're probably pulling it with like a rope at some angle. So we'd be talking about the vertical component of that applied force. But regardless, if the force is perpendicular, or anything that's not parallel, really is what we're saying, then that force is doing zero work on that system. They must be parallel. Same direction is adding energy, positive work. Opposite direction is going to be removing energy. Not parallel, anything that's not parallel is going to be zero. Okay, so that's work in. So that's this. Work in. Okay, the sixth question, if I would have numbered them, which I should have, but I didn't. The sixth question is, what is the equation you would use to determine work done by friction? So it's a modified version of this, but instead of saying work, we talk about WF for work done by friction. And that's going to be plus or minus. However, with friction, it's always going to be minus the force of friction times displacement. Okay, that is the equation that we use for work done by friction. Okay, all this equation is a modified version of this. It's similar to this, but this is always going to be minus force of friction. With work in, you have to make the choice whether it's the plus or whether it's the minus. Now, there's really two different reasons why it's always going to be negative. The two reasons are friction, the main reason, I guess I should say, is friction always opposes motion. Okay, friction always opposes motion. Whichever direction the object's going, friction is pushing in the opposite direction. No matter which way it goes, friction always is going in the opposite direction. If the object is moving right, friction is left. If the object is going up, friction is down. It always opposes motion, which means that they're always going to be in the opposite direction. Therefore, it's always going to be negative. The other thing about friction is when we talk about adding or removing energy from the system, friction is also going to remove energy from the system. Okay, so friction is always going to remove energy from the system. Friction never makes an object go faster. Well, here, I guess when we talk about energy, let's kind of quickly go back. This is not answering any of these questions, but when we talk about energy, what we're talking about is we're talking about mechanical energy. We're talking about kinetic energy. We're talking about gravitational potential energy. We're talking about potential elastic energy. Those are the three types of energies we're talking about. So when we say that we're adding energy to the system, there's three types we could add. We could add kinetic, means it's going to go faster. We could add gravitational, which means it's going to go higher. Or we could add elastic, we're going to compress a spring, or stretch a spring. Or we could remove energy from the system, which would mean I'm making something go slower, it's going lower, or it's less compressed spring. So those are the types of energy that when I talk about adding energy or removing energy, I'm talking about the combination of those. So it could do a couple things. We could be adding speed but losing height. Okay, there's kind of the combination. But most of the time when we talk about friction's generally going to slow something down. It's going to remove that kinetic energy component of that object. So this equation is one that we use a lot of. That equation is an equation that we use a fair amount of. Because we talked about, originally in that packet, there were four types. Work in, work done by friction, work done by normal force, we said it was kind of a silly one because as soon as you lift it, there is no normal force, therefore normal force is, in our situations, because we don't use any angles, is always going to be equal to 0. And the work done by gravity is something that we can, is absolutely a thing, but we can get that work done by gravity by talking about gravitational potential energy and what's our change in gravitational potential. So this equation and this equation are really the two work equations that we need to know. Those are the two that we really need to know and be able to use. Now, at the beginning of the unit, or on that worksheet, maybe it was the next day actually, now that I'm thinking of it, we talked about if it's a two-location problem, the equation that we use is this equation. This is our two-location problem, location. Work in plus work done by friction is equal to change in our mechanical energy. That's number 8. That's what we use when we use our two-location problem. If there was no work in, and if there was no work done by friction, then we could say ME1 equals ME2. It's a modified version of that. If this was 0 and this was 0, ME1 equals ME2. But that's our two-location problem. Right there is the two-location problem that we're going to be using in this unit. Because now we will have work in, or we will have work done by friction, which is going to cause your mechanical energy to change. It's going to either increase or it's going to decrease depending upon the situation. If I give you a push, I'm applying a force over some displacement, you're going to go faster, right? If we're going sledding, the top of George Street Hill, and if there was no friction and I don't push you, ME1 equals ME2, we go down the hill. However, if we're at the top of the hill and I give you a push, you're gonna be going faster at the bottom of the hill because I added energy to the system. I added energy, I put some work into the system. Now in reality, we know that there is friction on a sledding hill. Therefore, you're gonna actually slow down because friction's gonna slow you down. So this is our two equation problem. Number 9, I'm just kind of expand this out. The idea of number 9 is if we were to take this and we kind of fully work this out, work in plus work done by friction equals change in mechanical energy. Change in mechanical energy is when we take our mechanical energy at location 2, my final mechanical energy, and I subtract it from the mechanical energy that we start with at location 1. Same idea as ME1 equals ME2, we're just now talking about it on the same side of the equal sign. And it's the difference between those two. That's what delta ME means. If we do a quick substitution, we can then say for number 9, this is not the fully expanded version, we're gonna work this out kind of as we go. We can say work in plus work done by friction, but instead of saying delta ME, we can say that that's ME2 minus ME1. Now number 9 is not asking what is ME2 minus ME1, it's saying what if we fully expand all of the energies that we have. And what I'm saying is, go back to ME, we said ME is equal to KE plus PEG plus PEE, and that's ME. Now what we can then do is we can do yet another substitution, and we can do another substitution, and what we find out is that work in plus the work done by friction is equal to, but now instead of saying ME2, we can say ME2 is going to be my kinetic energy at location 2 plus my gravitational potential energy at location 2 plus my potential elastic energy at location 2. That's my ME2. And I'm going to do this in a separate color, minus my ME1, and instead of saying ME1, we can say ME equals KE plus PEG plus PE, parentheses, KE2, KE1 plus PEG1 plus PEE1. Okay, that, number 9, is my fully expanded two-location problem with energies. So this is the problem, the equation that we start with. This is the equation that we fully expand it out to. And when we do problems like this, I'm going to start with this equation. And right from this equation, I'm probably going to jump to this equation. It's just a couple substitutions, right? Change in mechanical energy, final mechanical energy minus initial. How do we find mechanical energy at location 2? Well, we take these 3 types of energy and we add them together. Minus, how do we find mechanical energy? We add these 3 mechanical energies together at location 1. Now notice, I color-coded on purpose. Order of operations, math stuff. See, now you know why you took math classes all these years, so you could do physics.
Oh yeah.
Yeah, you're welcome, math department, for justifying. Just kidding. Just kidding. So, so order of operations say I have to do the stuff in parentheses. So I got to add my greens together. Then I got to do the stuff in parentheses. I got to add my black numbers together. Then I take the difference of those. Make sure you do the sum of the blacks, the sum of the greens, and then do the subtraction of those 2 things. if you simply subtract KE1 and then you add PEG after it, it's going to be wrong. You got to add the sum of, because that's what mechanical energy is, the sum of our energies, which is kinetic and gravitational and elastic potential energy at that location. Just don't screw up that algebra. Silly algebra 6, so don't do it. Okay? The last kind of definition, or I'm sorry, that is what the next question is asking, is definition. There's really one more calculation that we'll do, or like formula-wise, and it deals with the term for power. So when we talk about power, it's a way that we can kind of determine, well, here, let's start with the definition. So number 10, when we define power, power is the rate at which work is done. Rate means like how quickly, the rate at which we do work. It's the rate at which work is done. So in terms of formulas, I think that's what number 11 is asking next. The formula for work is P, capital P, is equal to capital W divided by T. And capital P stands for power and is measured in watts, or we can use a big W, and I know that's it's slightly confusing, but I'll try to clarify. This W stands for work, and that's measured in joules, and my T stands for time, and that's going to be measured in seconds. So it's not my fault, so don't blame me. Just be aware of it. When we talk about power, power is measured in watts, which can be abbreviated with a capital W. But this W is a unit, right? It'd be 500 W. There'd be a number with a W next to it. The unit, which goes behind a number, is not the same as the variable for W, which is for work. So yeah, just be aware, work, this W is a variable that stands for work. This W is a unit that represents how much power. Okay, so number 12, I think, is the question, like what units do we use for power? And it's watts. If we continue our numbering onto page 2, which I didn't number the pages either. What is the unit for power? It's watts. We measure power in watts. So anybody think of a place where you see watts listed?
On the back of J.J. Watt's jersey.
Yup.
Electrical.
Electrical, jersey, good. I was thinking the electrical, but you're right. So, like, specifically when you talk about electrical, like what?
Like the current, how much electricity is running through it.
Like of what though? Give me an example.
Light bulb.
Light bulb, right? Light bulb is probably the most common thing that we see. Okay, like once upon a time, back in the good old days, there were these light bulbs that would like burn your hands if you touched them, called incandescent light bulbs.
That sounds like a good old day.
It was a good old day. You'd like, yeah, glass, ouch, burn, drop, shatter. It was like a double thing. You burned your hand and you cut your hand and you stepped on broken glass. It was, yeah. You turn it off for a couple seconds and it helped, or you wait like a minute and it was cool, but anyway. Incandescent light bulbs were these things, and probably you still have some incandescent light bulbs in your house. They're this traditional glass light bulb. They get really hot. And the reason why they get really hot is you take an electric wire, you run a current of electricity through it, and it glows really, really bright white, and it produces light. Thomas Edison, the filament of the light bulb, was the guy who came up with, I think it's tungsten is what we use. That was what we typically use, like a 100-watt light bulb, 75-watt light bulb, a 50-watt, 60-watt light bulb. And the idea is that's how much energy energy, work, is joules, right? How much work is done or energy is used per unit of time. So a 100-watt light bulb would use 100 joules per every second. If you had a 60-watt light bulb, it would be 60 joules per second. So it would use less electricity because it's only 60 watts versus 100 watts. But it was also not as bright because you weren't running as much electricity through it. Fast forward quite a few years from Thomas Edison's time, we started using those spiral compact fluorescent light bulbs, which use less electricity, and then LED technology has really come a long ways. The difference between a compact fluorescent and LED isn't as significant. I think there is a slight electrical energy consumption advantage by using LEDs. I think they use a little bit less light than a compact fluorescent, not a lot, but their lifespan is supposedly much, much longer. So a lot of like these lights in our ceiling are now LED, because they use less electricity. So like, I used to, like a 60-watt incandescent light bulb used to, like a compact fluorescent was like 13 watts. And I think an LED was maybe like 10. So it's a little bit less, but it's what we measure that. Now, sometimes when we talk about chargers for like iPads and stuff, depending if you're buying like a aftermarket one, they might have a wattage, you know, like a 5 watt, 12 watt, 20 watt. I don't remember even what the wattages are. I think this is I think your iPads are a 10 watt. It's a 12 watt charger, I think. But that's another way to measure is like how much power is being used or produced, I guess. Okay, so that's what we measure with it. Now, when we talk about power and calculating power, sometimes time is given, but sometimes we might have to do a Fab 5 problem to determine time. Or maybe we use a stopwatch and we say, and Mark said, go, and we time that event. But you need to know the time in order to produce a power calculation or to do a power calculation. But if you know work and you know time, it's just simply dividing those two numbers, and that'll give you your power points. All right, let's do a couple calculations, and we'll see kind of how far we get. So, moving on to number 12. Number 12, we did number 12. Number 12 is watts. 13, if a person pushes a 10 kilogram object to the right with a force of 30 newtons, for how many meters?
8.
8 meters, thank you. For 8 meters, how much work did they do? I would encourage pictures, kind of free body stylish, not necessarily, but a lot of the same things. So we have a 10 kilogram object is being pushed to the right. I would consider that to be an applied force of 30 newtons to the right. And it does tell me that it's moving a displacement, a delta x of 8 meters. And it's being pushed to the right, so it does also tell me the direction is to the right. Now, are there other forces acting on this object? There maybe, perhaps. Perhaps. There's a normal force, for sure.
There's gravity.
And for sure, there is a gravitational force. We don't care about those three forces at this point in time, though. Okay? And the reason is, the question is not asking what is the normal force, what's a gravitational force, is there a force of friction, what is the force of friction? It doesn't tell us whether it's a frictionless or frictioned surface. It's just saying how much work did that person do? What I'm asking you is, what's the work in? That's really what's being asked. And all we have to, in order to calculate that, I shouldn't say all we have to do, in order to calculate that, we use the work in, I think it was on line number 2, or question number 2, was plus or minus our applied force times the displacement. our work in is equal to, I'm gonna leave a blank because I'm gonna come back to this plus or minus in just a moment, is going to be our applied force of 30 times our displacement of 8 meters, and that'll give us our work in. Now we need to make the choice, is it the plus, are we adding energy to the system by pushing it? Or is it minus, are we removing energy from the system when we push it? And the way we know that is based upon the force was to the right, and it said the displacement is to the right. And I don't remember which question that was. It was 1, 2, the third one. If they're in the same direction, then it's going to be, what?
You were talking about the front page?
Front page.
Can be.
If my applied force is to the right and my displacement is to the right, it's gonna be plus, or is it gonna be minus?
Oh, it's plus.
It's gonna be plus. So by pushing this object to the right, and the object moves to the right, we are adding energy to the system, and we are adding 240 joules worth of energy to the system by adding work. Now, is it possible to push in the opposite, to push on an object that's opposite from the direction it's going?
Well, yeah.
Yeah, right? It's possible. You gotta keep moving as well, so you don't get like squashed by the thing. But it is possible, right? I can be pushing on something this way, and the object's moving this way, but what I'm doing is I'm like slowing that thing down by doing so, right? My car is rolling down the driveway. Ah, I forgot to put it in park. Okay, I'm pushing on the car to try to slow it down as it goes down the driveway. I'm removing energy from that system. I'm trying to slow it down actually to stop it. Two people are, I don't know, I was gonna say fighting, but we don't fight. We push on each other.
Fighting is wrong.
Right, so, I don't know. One person's pushing this way, one person's pushing this way. They're trying to share their opportunities to eat, I don't know, lunch? It's not working. Drop that. Okay, if two people are pushing against one another and one person's pushing this way and the other person's pushing this way, the idea is this person is pushing this way. However, they might be going this way because their friend is stronger than they are. Or they're letting them win, whatever you want to talk about. Okay, so positive versus negative. So it is possible to remove energy from the system. It's when you're forced in the opposite direction as the displacement. Number 9, nope, not number 9, that's a dot on top of that one. Number 14, it looks like, number 14. Okay, so number 14 is now given some information, given some work. We should be able to then do the other one. Okay, so now what we have is for number 14, we have a person and 500 joules of work. A person does positive 500 joules of work on a 5 kilogram object over a distance of 4.5 meters. How much force? So the idea is a 5 kilogram object, there's some applied force. I don't know how much. There's some displacement, which is equal to 4.5. I'm gonna say it's to the right. Person does work over a distance of, okay? And it's saying the work in is equal to a positive 500 joules. So the work in equation is equal to plus or minus our applied force times displacement. Now, the fact that this is 500 tells us that which one of those is that going to be? The positive, right?
Yeah.
So if this is positive 500, then is it the plus or is it the minus? It's the plus. Our applied force is the thing in question times the displacement. And I think that's, I don't remember. Is that one? my applied force is equal to 111.11 newtons.
That's a lot of ones.
It is, and it's actually repeated one, I guess kind of round, I'd stop, but yeah, it's a repeating one actually. We're gonna do two more. Number 15 is now using that power equation. Power is equal to work divided by time. That's the equation we're gonna use, because the one that would have been number 15, if there were numbers on it, says, if a person does 500 joules of work in 10 seconds, how much power do they do? If they do 500 joules of work, that's my work in. If it takes them, if they do that in 10 seconds, that's our time. So power is equal to work divided by time. Our power is equal to 50 watts. So how do we determine the work in? This time it was, it was given, but if we knew applied force and a displacement, we could determine that. But we can also determine it in a two location problem. So in that really long drawn out equation, where they talked about work in plus work done by friction is equal to ME KE2 plus PEG2 plus PEE2 parentheses minus parentheses KE2 plus PEG2 plus PEE2 parentheses, we could solve for that work in there. And if you know work in and your time, you can then determine power. So on the very last page, we're going to jump to that calculation. This is a calculation very similar to what you're going to do in class on Wednesday. So on Wednesday, we are going to climb a flight of stairs and determine how much power you produce by doing that. So this problem is similar, except for we're going to scale ours down slightly. However, there used to be a race, I don't know if it still is a thing, they used to have a race to the top of the Sears Tower, now called the Willis Tower. In Chicago, it used to be called the Sears Tower. Probably not in your lifetime, it's now referred to as the Willis Tower. And what there would be is there was a race that people would, I think it was one of those like you raise like money for a charity and then you go climb and then it's a kind of a fundraiser. But there are competitive people who this is what they do. There's competitive stair climbers. Matthias Jahn is, I never took German, but is that kind of close? J-A-H-N, is that how you'd say that, Jahn? Sure, okay. He had the record that he set in 2009 by climbing 2,109 steps in 13 minutes and 9 seconds. Okay, so we can go through and determine how much power he is. Now, some of this stuff I looked up because he had a website. I don't know if he still has a website. By the way, Matthias prefers right-hand turns, so when he goes up the stairs, he prefers to grab that staircase and go like this. He doesn't really like these turns. Just so you know, if you ever meet Matthias. But the idea is it's going to be similar to what we're going to do. Is we're going to start on the bottom of the stairs and we're going to go up and then we're going to go up and then we're going to go up, and we're going to end up here at this location, and we're going to be a two location problem. And when he gets to the top, he's going to do the Rocky on top of the steps thing, like, yay, I did it. I used to always say, like, yo, Adrian, I did it, but he didn't actually, I think he didn't actually yell that when he climbed the stairs. That's part of some, like, movie, like, music kind of scene. There's not actually words during that part, but it's a two location problem. And when we're doing these two location problems, we're looking for a lot of the same stuff. We are looking for the same stuff that we looked for when we did ME1 equals ME2 problems. we're looking for heights, we're looking for velocities, we're looking for spring stuff. But the other thing is, we're also looking for forces. We're looking for friction, and we're looking for work applied force. Now, this is not a conservation of mechanical energy. This is not Matthias stands on the bottom and all of a sudden ends up on the top, right? He has to apply a force to get to the top of the stairs. Now, if he were to fall down the stairs, that could be an ME1 equals ME2. Technically, he's gonna lose, every time he hits the next step, he's gonna lose some energy due to friction, but that'd be a different situation. So is this ME1 equals ME2 problem? The answer is no, because he has to put some work in order to get to the top of that flight of stairs. But we can still compare those two locations in order for us to calculate that work in. So when we go through, and we can say, is there any friction? For our sake, we're gonna say there is no friction. A little tiny bit of air resistance probably is gonna slow them down ever so slightly. But when you climb 2,109 steps, the amount of air resistance is probably pretty minimal. I would assume pretty minimal. But what we're trying to do, ultimately we're trying to determine power, and in order to do that, we're gonna have to take work, specifically the work in, and we're gonna have to divide by T. And the way we're gonna calculate that work in is using the long equation, as sometimes referred to as. Because there's no work done by friction, we can say work in plus 0 is equal to change in mechanical energy, which is my final mechanical energy, ME2, minus my initial mechanical energy, ME1. Now we expand these out. Work in is equal to ME2. Remember, ME is how much kinetic at location 2, plus gravitational potential energy at location 2, plus how much potential elastic energy at location 2. That's my ME2. Then we need to subtract from my ME1, and how do we calculate that? The exact same way, where we add my KE1 plus my PEG1 plus my PEE1, and that's what we get for our long equation. Now we've already canceled, I should say, the work done by friction because we said that was 0. And once we get here, well, I guess let's take a step back. We've talked about the questions, like, hey, is it moving? Is there a height? Is there a spring? That's the same idea. We're going to use those exact same questions for our energies. The questions that we can ask ourselves for here, is there an applied force in the displacement? We need both. Is there an applied force? If no, we cross it off. And is there friction? If no, we can cross it off. So we have to kind of make some assumptions here. So it's a race, so on your mark, get set, go. How fast is he going before the stopwatch starts? Matthias is a world-class stair climber in a race. He is not going to cheat. So therefore, his initial velocity would be 0 at location 1, which means his KE1 is going to be 0. If we choose, which would make sense, the bottom of the staircase to have a height of 0, then his PEG1 will be 0. Is there a spring?
No.
Unless he has some springs in his shoes, which we're going to pretend like there's no such thing, that would also be 0. Now at the top, once he gets to the top, he's not going to be moving anymore. There's no more steps for him to go up. Does he have a height when he's at the top? Absolutely, to be determined what that is, and there's not going to be a spring. Now, how do we calculate his height? Now, I could have just looked up the height of the Sears Tower and how far is it from the ground floor to the sky deck, which I did. But that's not how we're going to do in class, because it's really hard to measure that distance. So what we, of course, we have to do is we have to measure a step, and each step that Matthias takes is 0.195 meters, it was 19.5 centimeters, 0.195 meters tall, and every time he went up, he counted, and he emailed me. Actually, he didn't email me about that, but he told me, he didn't tell me, I looked it up, divided by, I looked up the number of steps, but the story's a little bit. Then we can determine what the total height that he climbed. So 0.195 times 2,109. His total height that he climbed was 411 meters. I'm sorry, there's a decimal there. 411.255 meters. So basically, you take the track, you straighten it all out, and he went straight up one lap, is what he did, in 13 minutes. I can run around the lap in 1 minute. I can't, but I can pretend like I could. Remember, he went straight up, though, and it took him 13, so I'd say he did pretty good. So, yes, he has a height. So when we determine this work in, PEG is going to be his mass times G times H. Now you could say, how in the world do you know his mass? Well, I could make it up, or I could email him and ask him, which is actually what I did do back in 2015. I emailed him off of his website, and I said, hey, I have the email. I just don't have time to show you right now. Hey, Matthias. And the attempt on your world record climbing attempt, we're trying to calculate your power output. Approximately, what was your mass in kilograms at the time of your race? Hi, Tom. At this time, I was not kidding. I really did email him, and he really did email me back. It's probably a weird email to send, but I didn't really care. It was around 63 kilograms. Thank you, Matthias. We're like besties now. This is pre-Snapchat. Otherwise, he'd probably be following me on Snapchat right now because of this like non-awkward email that I sent. He'd be like, oh, that totally seems like a guy I want to follow. Right? Is that what you do? You follow on Snapchat? Is that what you do? I don't even know. Whatever.
Just kind of have people on.
Yeah, you kind of have friends and stuff.
I don't have any friends on Snapchat. I don't have any Snapchat friends.
Oh, well, I was gonna say.
Or any friends, other friends that might be there. But that's
What are friends?
Yeah, honestly.
all right. So when you take those numbers, assuming I did my calculation, I plugged in my calculator right, that's how much work he did. 253,908.837 joules. And then to calculate his power, the last step is taking that work, 253,908.837, and divide by the time. It's on that O sheet. What's the seconds?
789.
789 seconds?
Yeah.
And it's right around 300 something.
321.81.
Power is what?
321.81, I believe.
81 watts.
Yeah.
My guess is you will produce more watts than Matthias when you climb the stairs. But he did it for 13 minutes. You're going to probably take like 20 seconds. So,
Wow.
but that's the idea, okay? We didn't get as far as I had wanted us to get today. We did it was a lot of me talking. Thank you for your patience, and I appreciate that. I do not have a virtual day assignment just because we didn't get quite where I had wanted. So it's in the start of the new semester, blah, 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 team building, wait, I'm recording this part. I shouldn't be lying on that. So we have no virtual day assignment for tomorrow. We will pick up on Wednesday.
Okay.
Okay?
That's why I like the